Good afternoon, everyone. Good afternoon, sir. My topic for this session is about unique factorization theorem. Before we start, let me introduce first my intended learning outcomes. At the end of the session, the mathematics students should perform unique factorization. In number theory, the fundamental theorem of arithmetic, also called the unique factorization theorem or unique prime factorization theorem, state that every integer greater than 1 either is a prime number itself or can be represented as a product of prime number. X is an element of the sets of all positive integers such that x is greater than 1 where number x is a product of p1, p2, p3, so on until pn, where p is a prime number. For example, 30 is a number greater than 1 and can be represented by a product of prime number such as 2, 3, and 5. The list of factors can have the same prime number on it more than once. Example, for number 100, the prime factor of number 100 are 2 times 2 times 5 times 5, or 100 is equal to the square of 2 times the square of 5. Notice that the prime number 2 and 5 were repeated twice. If you change the order of number in the list, it's still considered to be the same list. For example, for number 1000 is the prime factor of number 1000 are 2 times 2 times 2 times 5 times 5 times 5. Can also be written as 1000 is equal to 2 times 5 times 2 times 5 times 2 times 5. This means that the orientation of the prime factors does not affect the value at all, as long as it contains the same prime factors and the same number of its factors. Unique means that is only one possible list of prime number factor for any original number. For example, the number 150 can only have prime factors of 2, 3, 5, and 5, and no number has the same prime factors and number of its factor. I have here an example of prime factorization. Since it is stated that prime factorization is also called as a unique factorization, we take 100 as our example, and by using our factor tree, we break down number 100 into each prime factor. We use 2 as our prime factor since 100 is factorable by 2. 100 divided by 2 is equal to 50. 50 is a factorable number, so 50 is divisible by 2. So 50 divided by 2 is equal to 25. Another, 25 is a factorable number. Since 25 is factorable by 5, so 25 divided by 5 is equal to 25. 100, the prime factor of 100 are 2 times 2 times 5 times 5, or 100 is equal to the square of 5 times the square of 2. This example satisfy our first theorem, which is n is greater than 1, which is 100 is greater than 1, and the product of p1, p2, p3, so on until pn. Another example of prime factorization is the number 1000. We take by using our factor 3, and we break down 1000 into each prime factor. Since 1000 is divisible by 2, we take 2 as our basic prime factor of 1000. So 1000 divided by 2 is equal to 500. Since 500 is factorable number, so 500 divided by 2, since 2 is divisible by 500, is equal to 250. 250 again is a factorable number, so 250 is divisible by 5, so 250 divided by 5 is equal to 50. then 50 is divisible by 5 again. So 50 divided by 5 is equal to 25. Then 25 is divisible by 5. So 25 divided by 5 is equal to 5. So the factor of 1,000, the prime factor of 1,000 are 2 raised to the third power times 5 raised to the third power. So this example satisfies also the theorem of unique factorization that a prime factor repeated not only once. The third example of prime factorization is 990. So 990, we break down this 990 into each prime factor. So 990 is divisible again by 2. So 990 divided by 2 is equal to 495. Then 495 divided by 5 is equal to 99. Since 99 is divisible by 11, prime number 11. So 99 divided by 11 is equal to 9. Since 9 is a factorable number, so 999 is divisible by 3. So 9 divided by 3 is equal to 3. So the prime factor of 990 are 2 times 5 times 11 times 3 times 3. Or we can rewrite 990 is equal to 11 times 5 times 3 times 3, which satisfy also the theorem of unique factorization that if we rearrange the prime factor of a certain number will give us the same product. Okay, another example. A simple way of visualizing and remembering the theorem is to think of the list of prime factors as being a recipe for a number. There's only one recipe for any given number. The one and only recipe for number 44. Ingredient, we have two number 2's, one number 11, then the direction. Combine the ingredient by multiplying. Use immediately or save for later. Although it seems easy to factor an integer, it is actually not always. Generally, if the number has only small factors, then it is not hard to factor. But if the number is very large and has only a few large factors, then there is no efficient algorithm clearly available. Okay, for the evaluation, I have here 5 numbers. Give the unique recipe for the following given numbers. Thank you and God bless.